Signals and Systems Homework Help. For any homework-related queries, call us at +1 678 648 4277. You can mail us at info@matlabassignmentexperts.com, info@matlabassignmentexperts.com, or reach us at https://www.matlabassignmentexperts.com. https://www.matlabassignmentexperts.com, matlabassignmentexperts.com. Problems. 1. Consider an inverted pendulum mounted on a movable cart as depicted in figure P26.1. We have modeled the pendulum as consisting of a massless rod of length L, with a mass m attached at the end. The variable 0, t, denotes the pendulum's angular deflection from the vertical, g is gravitational acceleration, s, t, is the position of the cart with respect to some reference point, a, t, is the acceleration of the cart, and xt represents the angular acceleration resulting from any disturbances, such as gusts of wind. MatLabAssignmentExperts.com. Our goal in this problem is to analyze the dynamics of the inverted pendulum and more specifically to investigate the problem of balancing the pendulum by Judy Sias' choice of the cart acceleration a, t. The differential equation relating 0, t, a, t, and xt is This relation merely equates the actual acceleration of the mass along a direction perpendicular to the rod and the applied accelerations, gravity, the disturbance acceleration due to xt, and the cart acceleration along this direction. Note that EQ P26.1-1 is a nonlinear differential equation relating 0, t, a, t, and xt. The detailed, exact analysis of the behavior of the pendulum therefore requires that we examine this nonlinear equation. However, we can obtain a great deal of insight into the dynamics of the inverted pendulum by performing a linear analysis. Specifically, we will examine the dynamics of the pendulum when it is nearly vertical, i.e., when 0, t, is small. In this case, we can make the approximate imations. MatLabAssignmentExperts.com. Suppose that the cart is stationary, i.e., a, t, equals 0, and consider the causal LTI system with input xt and output 0, t, described by EQ P26.1-1, together with the approximations given in EQ P26.1-2. Find the system function for this system and show that it has a pole in the right half plane, implying that the system is unstable. The result of part A indicates that if the cart is stationary, any minor angular disturbance caused by xt will lead to growing angular deviations from the vertical. Clearly, at some point these deviations will become sufficiently large that the approximations of EQ P26.1-2 will no longer be valid. At this point, the linear analysis is no longer accurate, but the fact that it is accurate for small angular displacements allows us to conclude that the vertical equilibrium position is unstable, as small angular displacements will grow rather than diminish. B. We now wish to consider the problem of stabilizing the vertical position of the pendulum by moving the cart in an appropriate fashion. Suppose that we try proportional feedback with a t equals ko t. Assume that 0, t, is small so that the approximations in EQ P26.1-2 are valid. Draw a block diagram of the linear system with 0, t, as output, xt, as the external input, and a, t, as the signal that is fed back. Show that the resulting closed-loop system is unstable. Find a value of k such that if xt equals 5 t, the pendulum will sway back and forth in an undamped oscillatory fashion. MATLABassignmentexperts.com. C. Consider using proportional plus derivative (PD) feedback. Show that we can find values of K and K2 that do stabilize the pendulum. In fact, using G equals 9.8 m/s, L equals 0.5 m, choose values of K and K2 so that the damping ratio of the closed-loop system is 1 and the natural frequency is 3 radian per second. 2. Consider the feedback system given in Figure P26.2. MATLABassignmentexperts.com. A. The closed-loop system is a new second-order system. Find the new natural frequency and the new damping factor K for K equals 1. B. Find the poles of the closed-loop transfer function. C. Sketch the trajectory of the poles as K goes from negative infinity to positive infinity. 3. Consider the system in Figure P26.3. MATLABassignmentexperts.com. C. For what range of values of A, 0, and R will both H1, S, and H2, S be stable? 4. Consider the feedback system in Figure P26.4. Find the closed-loop poles and zeros of this system for the following values of K: A, K equals 0.01, B, K equals 1, C, K equals 10, D, K equals 100. MATLABassignmentexperts.com. 5. Sketch the root loci for K greater than 0 and K less than 0 for each of the following systems: A, B. MATLABassignmentexperts.com. 6. Consider again the discrete time feedback system of example 11.3 of the text, page 712. The root loci for K greater than 0 and K less than 0 are depicted in Figure P26.6. A. Consider the root locus for K greater than 0. In this case, the system becomes unstable when one of the closed-loop poles is less than or equal to -1. Find the value of K for which Z equals -1 is a closed-loop pole. B. Consider the root locus for K less than 0. In this case, the system becomes unstable when one of the closed-loop poles is greater than or equal to 1. Find the value of K for which Z equals 1 is a closed-loop pole. C. What is the full range of values of K for which the closed-loop system is stable? MATLABassignmentexperts.com. 7. In this problem we consider several examples of the design of tracking systems. Consider the system depicted in Figure P26.7. Here HS is the system whose output is to be controlled, and HES is the compensator to be designed. Our objective in choosing HS is that we would like the output YT to follow the input XT. Specifically, in addition to stabilizing the system, we would also like to design the system so that the error ET decays to 0 for certain specified inputs. MATLABassignmentexperts.com. Suppose that. Show that if HES equals K, which is known as proportional or P control, we can choose K to stabilize the system so that ET goes to 0 if XT equals BT. Show that we cannot get ET minus 0 if XT equals UT. B. Again, let HS be as in EQ P26.7-1, and suppose that we use proportional plus integral PI control. Show that we can choose K and K2 to stabilize the system, and we can also get ET minus 0 if